In oxidation-reduction chemistry, redox, there's the idea of electron transfer resulting in something being reduced, a decrease in oxidation state, and something else being oxidized, an increase in oxidation state. And a fundamental idea behind that is, what is the oxidation state? What are the values that are assigned to those species? For an ion, it's very straightforward. It's the charge. For elements in a covalent compound, it's a little more work, and it's easily summarized as trust some things more than others. Some elements have fewer options. So you can look in many textbooks, and there's many, many, many rules, but I think we can kind of break it down into 4.5 rules or so. The first thing, and I'm not even going to call it number 1. This is so baseline, we're not going to give it a number. Elements, things in their elemental state, have an oxidation number of 0. Okay? So elemental state, you have the oxidation number equal to 0. Right? And how are we going to spot things in their elemental state? There are things that don't have a charge, and there are things that aren't in compounds, except for the diatomics. But is it in its elemental state? Well, is it in a compound? Does it have a charge? If both answers are no, it's in its elemental state, and its oxidation state is going to be 0. Okay? Now, there's one element on the periodic table that can do whatever it needs to, the energetic driving factor and its size and everything else, and that's fluorine. Fluorine's in group 17. We would predict it to be a 1-, and when it's in a compound, it's a 1-, period, every single time. So if you have fluorine in a compound, it's going to be 1- every single time. So this is our hierarchy. We're working our way down in terms of what we trust and what we don't, so we can use that to make predictions about other elements. Other things that we might trust, hydrogen. So hydrogen is usually 1+, right? And I think most people would predict that. It's in group 1 of the periodic table. It has 1 valence electron. What I don't think they necessarily predict is what happens when hydrogen's bonded to a metal, okay? So unless it's with a metal, which results in a hydride, a hydrogen with a 1- oxidation state. So that's a hydride, we call it. So we have hydrogen, and I think very commonly an element that people trust, and I know that's weird terminology, but an element that has very predictable behavior is oxygen. And it's usually 2-. It's group 16 of the periodic table. You expect it to gain 2 electrons, which will make it a 2-. It has options, though. In fact, it has options that you don't expect at all. And then our 4th rule, and this is really the catch-all, what if none of these rules apply? We're going to trust, and again, that's not great terminology, right? We will rely on the elements that are more predictable, that have fewer options. And those elements are in group 1 or closer to group 1, or group 17 or closer to group 17. And if they're in the same group, we have to go by which one's closer to the top. And I know that's a lot, so let's look at this. Trust elements in group 1. Well, in fact, let's say closer to group 1, right? Group 17. And what if they're both in the same group? And we might say closer to the top of the periodic table. All right, and that applies to things that are in the same group. So if you had to choose between nitrogen and phosphorus, you'd say, all right, well, nitrogen's closer to the top. That's the one I'm going to have more confidence in its behavior. All right, so the idea is options. Group 1, you expect to lose 1 electron and become a 1+ cation. Group 17, you expect to gain 1 electron and it'll become a 1- anion. And if you look at like group 14, you might say, well, carbon could be a +4 or a -4. And I think that then you have to start making decisions. And you can rely on the things that you're more confident in, the things that have fewer options. And then you can use those to find out about the things that you're less confident in. So let's take a look at the actual assigning of some oxidation numbers. I'll have to erase this, but and we'll start with something fairly straightforward. And the way I lay this out, and a couple things to note, oxidation numbers and charges. Charges technically, so when you're writing a charge, it should technically be number then sign, right? Number then sign. When you're writing oxidation numbers, it's technically sign then number, or sign then number. All right? I'm not going to worry about that. For first year chemistry, or in fact, in pretty much any application, it's semantics, and it's not going to confuse anyone if you move the sign to one side or the other. So I'm going to leave the signs on the right-hand side of the numbers, and I'll mention one other slight change from many textbooks as we go. So if we're going to assign some oxidation numbers, right? Assign oxidation numbers to the elements in these compounds, all right? And we'll start with something fairly straightforward, and it's going to be like, well, I might have known that, right? So carbon dioxide, all right? Carbon dioxide has one carbon and two oxygens. We're going to follow our rules explicitly. First thing, is it in its elemental state? Well, there's a compound, nothing in its elemental state. Do we have fluorine? No. Do we have hydrogen? No. Do we have oxygen? All right, that's our best bet. That's going to be our basis for what happens. Oxygen, we expect to have an oxidation state of 2-. What you see here is nothing, because there is no charge on this compound. And I'll say that again a little slower. Right here you don't see anything because there's no charge on carbon dioxide. So I'm going to carry that no charge down as a 0. The sum of our charges have to add up to 0, or the sum of our oxidation numbers. I have two oxygens, right? So if each oxygen is a 2- oxidation state, and I have two of them, I'm going to end up with 4 minuses, all right? And if you look at that mathematically, you're just multiplying going down. 2- on each oxygen, because that's the one that we trust more. 2 of them gives me 4 minuses. And then it's just some algebra, which is, well, positive 4 plus 4 is 0. I have 4 total things, or 4 total positives. I've got 1 carbon to get me there. We're dividing to go in that other direction, and you get a 4+. All right? So these are our oxidation states, our oxidation numbers for these things. And the really, really key part here, not an ion, not an ion. This is a covalent compound, but that's what their charges would be, right? That's what their charges would be, and that's the basis of an oxidation state. Some textbooks, and in many instances, you might see this work flip-flopped with the oxidation numbers at the bottom. I don't like that as much, because when the oxidation numbers are at the top, we start thinking about them as charges. And if you're putting total oxidation states at the top, I don't think that's super intuitive. All right, let's look at the big picture a little bit here. I knew oxygen was going to be a 2-, right? Oh, carbon, I would have guessed plus or minus 4. Yeah, well, you had maybe a 50-50 chance on that. What if, though, instead of carbon dioxide, we had a compound very similar in formula, carbon monoxide, okay? Carbon monoxide. We're going to go through the same process. Is it in its elemental state, or are there things in their elemental state? Well, there's a compound. No charges, no. Is there any fluorine? No. Is there any hydrogen? No. Is there any oxygen? Yes. Then that's where we're going to start. Oxygen, we predict, will be a 2-, okay? There's nothing here. We have no charge, so this has to add up to a 0. I have 1 oxygen, so as I go down, 2 times 1 gives me 2 minuses. Now, how are we going to balance out 2 minuses? Well, it takes 2 pluses to balance out 2 minuses. I'm going to divide going back up. There's 1 of those carbons. 2 divided by 1 is 2+. All right? And those are our oxidation states. And as you look at it, carbon's a 2+ here, and you weren't expecting that. All right? There's no reason you necessarily would. You could explain it knowing that it is. Well, carbon's got 2 valence electrons in the p sublevel, and maybe it loses those 2 in some favorable situation, but you wouldn't predict it. The analogy I also always use is like if I had a suitcase full of cash and I gave it to some kid and put him on a plane to Vegas, would you trust him? Versus if I gave that same kid a suitcase full of cash and put him in an empty bank vault, would you trust him? And the answer is I'd trust him a lot more in that empty bank vault, because he has fewer options, all right? So oxygen, most likely a 2-. It's only got a couple options. Carbon, 4+, 4-. I don't know what it's going to do. And look, 2+, right? So here, maybe that kid went to Vegas. came back with more money, right? That's a scenario we might expect. Or came back with less money. That's a scenario we might expect. In this situation, though, like maybe he got on the plane and then turned around and got right back off the plane, right? I wasn't expecting that to happen, and there it is. And we're able to use this thing that has fewer options to predict the behavior of things that have more options, all right? So let's take a look then at a very simple one in case anyone's paying attention, all right? AU, gold. So we're going to go through our hierarchy, our oxidation state assigning scheme. Do I have anything in its elemental state? Yes. It's not in a compound. It doesn't have a charge. It must be in its elemental state. So it's got an oxidation state of 0, right? And in a, I guess, related example, what if we look at something like S2-, all right? And you can work through this math of this system right here, but it's an ion. It has a charge. Its oxidation state is 2-, all right? And if you want to see that in like some bizarro slow-mo, this is my charge. I will carry it down. It has to be a 2-, right? What will add up to a 2-? A 2- will, I have one of them. 2 divided by 1 is 2-, all right? And a related example, I guess, would be the peroxide polyatomic ion, which is a different scenario. If you have O2, 2-, that's the peroxide polyatomic ion from like hydrogen peroxide and things like that. We would go through this same process. I've got 2 as the total charge we need to have. That's 2 minuses, right? The only thing I can have down here is 2 minuses. And if we divide going up, right, that's 2 divided by 2, which is 1 minus. And you wouldn't have predicted that, right? That's like that kid getting on the airplane, getting to Vegas, and donating all the money to charity. You weren't expecting it. It was an option, though, right? They didn't have that option when they were locked up. So we have to rely on the information we're given. And sometimes things don't happen the way we expect. That's why we need to go through a seemingly complicated process, all right? We've done monatomic, and this is kind of polyatomic ions. We'll get into some more complicated ones in a bit, but let's look at a few other scenarios, like what happens if you have something that has subscripts on both of them, multiples of each element. So we'll start out with our same process. Anything in its elemental state? No. Any fluoride? No. Any hydrogen? No. Oxygen? Yes. That's going to be a 2-. I've got nothing here, so this is going to add up to 0. I've got 2 times 10 gives me 20 minuses, and then that has to be balanced out by 20 pluses. We multiplied to go down, we're dividing to go up, and like saying those words and writing this stuff isn't necessary. I think with a little practice you just say, 20 of those, 20 over 4, that's 5 of those, all right? So your oxidation states are a 5 and a 2, and the key difference here between those is that this first thing has a subscript on it, and we actually have to show that division. We have to do that extra division step. If you're wondering why so many examples end up with oxygen, like I think I gravitate toward those compounds because oxygen is the most abundant element on Earth, and we see those compounds more often. Right? It's obviously a flaw in the way I do things. Let's take a look at a few other examples. In fact, we'll zip through maybe like 5 or 6 more. What about pH3? Kind of like NH3, ammonia and phosphorus is in the same group 15. So if I had to just make a straight guess, I would guess that phosphorus is going to be a 3-, hydrogen is going to be a 1+. Don't make assumptions, right? Sometimes things can do things you're not expecting. So we'll run through our rules again. Elemental state, no. Fluorine, no. Hydrogen, oh look, there's hydrogen, right? 1+, I've got nothing here, I'm going to carry nothing down. 1 times 3 is 3 pluses, going to be balanced out by 3 minuses. 3 over 1 gives me 3 minuses. Okay, yeah, that's what I would have predicted. But what about in a slightly different scenario with phosphorus again? Because phosphorus can do things that nitrogen can't, right? Things after the second period on the periodic table can start to break the octet rule with more than 8 valence electrons. So if you look at like PCl5, phosphorus pentachloride, okay? As we look at it, we can run through our rules and make some conclusions here. Nothing in its elemental state. I have a compound, I have no individual charges. No fluorines, no hydrogens, no oxygens. Okay, well our fourth rule was trust things that are closer to group 1 or group 17. And if you look, phosphorus is in group 15, chlorine's in group 17, I trust chlorine, right? And again, this idea of trust is kind of made up, but I think it's easy to conceptualize it that way. All right, chlorine group 17, 1 minus, got 5 of those, so that's 5 minuses, right? Nothing here, so it needs to add up to 0. 5 pluses is what it takes, divided by 1 is 5 pluses. These are my oxidation states, all right? So phosphorus group 15, you would expect a -3 if it was going to be an ion. It's a 5 plus, right? So maybe this kid with the suitcase full of money got on the plane, turned around, walked right back off. It was an option, right? We weren't expecting it, right? The behavior wasn't as obvious. And so we use things we trust more. Let's start to take a look at a couple polyatomic ions. Actually, let's do OF2 first, all right? Talk about things you don't expect. Here it is. So we check our rules. Anything in its elemental state? No. We don't see any charges, and we have a compound. Any fluorines? What? Yes, there's fluorine right there. That's a 1 minus. So we're going to have to add up to 0, right? And then we look over here. Well, that's 2 minuses. And what's going to balance out a 2 minus? 2 pluses, and there's one of them. Well, so that's a 2 plus. Oxygen's a 2 plus. It is, right? Like, it doesn't have a choice. It's acting as a 2 plus, at least in oxidation state terms, because fluorine's always a 1 minus. And like, it's a battle of electronegativity if you look at it in the big picture, but for right now, here's oxygen behaving as a 2 plus. Here's oxygen in a peroxide behaving as a 1 minus, and here's a bunch of oxygens behaving as a 2 minus, all right? So things aren't always as they seem, and I think that's really a surprising one, okay? Let's look at a few polyatomic ions. And then next time, we can take a look at redox reactions as a whole and breaking those pieces down. So, an active ingredient in bleach very often is sodium hypochlorite, or the hypochlorite ion, which happens to be a good oxidizer. You could see that as ClO minus or OCl minus, depending on how it's written. So we've got a polyatomic ion. And we did see an example of that previously. What's special about it is this, now we have something right here, and that's what we need to carry down, okay? So whatever we do over here needs to add up to a 1 minus. That's our charge on our ion. And so we're going to go through our rules. Anything in an elemental state? No. I've got a compound. Neither of those things have charges. Do I have any fluorines? No. Do I have any hydrogens? No. Do I have any oxygen? Oh, there's oxygen right there, yeah? So oxygen is going to be a 2 minus. And I have one of them, so that's 2 minuses. And here's our math problem, which is like, oh, something plus -2 is -1. That's a 1 plus. And I have one of those, so this has to be a 1 plus. And that's, again, something you weren't expecting, like that kid getting on the plane with a suitcase full of money and then getting off in Las Vegas and donating all the money to charity, right? You'd guess a 1 minus for chlorine, but here it is as a 1 plus in the hypochlorite polyatomic ion. And that affects the oxidizing behavior of the hypochlorite polyatomic ion. A couple quick other examples. If you've got like the hydrogen sulfide ion, HS minus, we can do this same process and we'll knock it out super quick here. We've got this that now we bring down, that's a 1 minus. We say, all right, no elemental state, no fluorine. Oh, there's a hydrogen. Hydrogen's a 1 plus, one of them, 1 plus. So then what's going to give us a 1 minus right here? Well, this has to be 2 minuses, right? And you might have predicted sulfur was a 2 minus, but here we have a confident statement of that. So we can try this one, and I think that this one is a little different and maybe a little trickier, so it's a good one to see. The cyanide polyatomic ion, Cn minus, which again, you've heard it maybe in poison or other things like that. It's a Lewis base. It's good at donating electrons, and Lewis acids like iron in your blood are good at attracting it. And so when you look at this interaction, like the reason cyanide is such an effective poison is that it's better at sticking to the iron in your blood than oxygen is, all right? So you ingest the cyanide and the iron starts carrying it around, instead of the oxygen, and then you die. It's a Lewis base, and that's a whole different conversation. So what's special about this example for us is not this charge, because we've done that before, but how our rules work out. Elemental state, no. Fluorine, no. Hydrogen, no. Oxygen, no. Uh-oh, right? So we have to trust one of these things more, and we said we're going to trust what's closer to group 1 or closer to group 17, and if you have to within the same group, choose something that's closer to the top. Well, in this case, carbon's group 14, nitrogen's group 15, 15 is closer to 17, so I'm going to take it. Group 15, I would expect a 3 minus, all right? And I have one of them, so that's 3 minuses. And what's going to balance out that 3 minus in this case is a 2 plus. So I have 2 pluses there, and we get the 2 plus and the 3 minus. And we wouldn't be as confident about that because nitrogen has options, carbon has options, but this is the compromise we have to reach in that prediction. So one or two other ones that I want to look at. We saw that the peroxide polyatomic ion had a 1 minus oxidation state. What about something like this, the tri-iodide ion? Okay, we can do this with our same process. I've got a 1 minus that I'm going to carry down, and that gives me 1 minus, right? And on this side, it has to be 1 minus. Now the catch is, when we go up, we're doing that division, and all of a sudden, it's a fraction. But that's okay. So you can do what it says. 1 divided by 3 is a 1/3 minus. Each of those iodines is acting as if it had an oxidation state of 1/3 minus. All right? So what we'll try to do later is take a look at this in terms of overall redox equations, looking at if it is redox based on things changing, or maybe it's double replacement, and then finding ways to balance redox equations, complicated ones using the half reaction method, and not complicated ones just by using reactant and product balancing tables.